Welcome to this, the 6th lecture in the Introduction to Radar Systems course, and this lecture is going to focus on radar antennas. And we're going to start the first part of the lecture now. Well, now we're back to our block diagram that we see at the beginning of each lecture. And you can see that the focus of this lecture is going to be on the antenna. And you can see that the antenna is the point where the electromagnetic energy leaves the radar and goes out into free space towards the targets that it wants to detect. And it's a very important part of the radar, a very important subsystem. And if we go down and look at the radar equation for track and for search, we see that antenna properties come into play very strongly. The signal-to-noise ratio of the target is proportional to the gain of the antenna squared. That's its ability to how well collimated the antenna beam is, the electromagnetic beam. How well that beam is collimated, how well we take the power of the transmitter and concentrate it in one direction. We'll go into explain to you what gain is. You can see that in the search equation, the area of the effective area of the antenna comes into play. They're very important properties. The system noise temperature and the losses that are connected with the antenna also come into play in the radar equation, and they were treated in the radar equation lecture, and we discussed those particular properties. But today we're going to focus on these properties which affect our radar performance in detail. Okay. So what is a radar, and how is it defined? Well, the IEEE, which is the Professional Society of Electrical Engineers, defines the antenna as the means for radiating and receiving radio waves, and that's quotes. A radiated electromagnetic wave, I want to remind you, those of you that aren't electrical engineers and haven't taken a lot of courses in electromagnetism, an electromagnetic wave consists of an electric and magnetic fields which jointly satisfy the equations that Maxwell developed in the late 1800s. And we're going to show you exactly how those electric and magnetic fields have to play. And notice it's a radiated electromagnetic field. And by that, it implicitly means that the energy in the electric and magnetic field are propagating out in space. And electromagnetic energy is propagating out in space. And they satisfy Maxwell's equations, which are the physical laws governing all electromagnetism. Now, the antenna is the transitional structure between the device that guides energy out of the transmitter, could be a cable, could be a waveguide, and free space. So the antenna is that device. And here we see a visualization of the electromagnetic waves in a very simple antenna, a horn antenna. And we could have exciting generating the electromagnetic wave, a source down here, typically a transmitter, and that could be just an accelerating charge. Could be a charge on a source that's going back and forth, oscillating, accelerating and decelerating charges, moving currents generate electromagnetic waves. And that wave will go down a metal guided wave, transition line. In this case, if the transmission line is a waveguide, it'll be metal on the sides, and the electric field vector, I'm showing you just now the electric field. The electric field vectors go, and they go from one piece of metal to another, one piece of metal to another. And then you see this section where the waveguide opens out, and that's called a horn antenna. And the electric field vectors bend, going from metal to metal, and the energy is pushed out. And when it's pushed out into vacuum, the electromagnetic field lines have to go back onto themselves. And this shows you what they'd look like near the antenna. and the energy is pushed out of the antenna in a certain direction. And the nature of how it's pushed out is determined by the design of that antenna. And I'm going to show you different designs. If you're an electrical engineer, you know about electrical circuits, and we can model all this stuff on the left by a circuit where we have a voltage source and its impedance or resistance, and that generates a source, and we send down a transmission line, a standing wave, and then the antenna can be approximated by a couple of resistances and a reactance. There's a certain amount of energy that we lose in the antenna as the electromagnetic wave goes through the antenna structure itself. The antenna heats up a little bit, and then there's the radiation that goes out. That R sub R represents the radiation that leaves. You'd like that to be most of the energy. And then there can be a little bit of energy, you want it to be a little bit, that just hangs around and as part of satisfying Maxwell's equation stays around right near the antenna. And that's the symbol XA is the reactance of that. So the antenna would be this part. If we were looking at it as an equivalent circuit, that's what it would be visualized by. Now, when we look at what the functions of the antenna are, there's about a half a dozen of them. As I said before, it's that transition point, the transducer between the transmitter and the free space. The next thing it does is it focuses the energy of the transmitter into a collimated beam so that you get lots of energy density on the target. We don't have energy going in all directions at once. In the introduction, we showed you an isotropic antenna with the energy going everywhere equally likely. We want the energy focused where we want it to go on transmit so the power will get out to the target. Likewise, when we're listening, after we've transmitted, we want the antenna to listen selectively at the angle where the energy is coming back from, that weak energy from the echo is coming back. So it also serves as the function of collecting very efficiently, by having a well-collimated receive beam, the energy from the echo. Okay? Another purpose of the antenna is to measure the angle where the targets that you see are located. If you have a very well-defined beam, think of it as a soda straw. And that'd be a soda straw would be a very well-defined angular beam in both azimuth and elevation in both angles, and you point that soda straw in a certain direction, you can say, aha, you know you've made a measurement. In fact, when you hear a target echo in your receiver, you detect it, you know if the antenna was pointing in that direction, that that's the direction of the target. So you're making a measurement of the azimuth and elevation that you can, depending upon the shape of the beam. If it's shaped like a soda straw, you'll get very good measurement in azimuth and elevation. Having that very good measurement in elevation and azimuth also allows you to resolve targets that are nearby an angle. If the targets are 2 or 3 soda straws apart or a couple of soda straws apart, you can resolve and say, gee, there are 2 targets near each other. So the antenna allows you to resolve targets also. It also has control, depending upon the number of soda straws that you have to transmit, so to speak. Before you've looked at all the space you want to, it tells you how much you have to revisit space. It tells you how long it's going to take to go through and transmit and receive at all the different area of angle space that you want to put out energy and search for targets. Okay? So it performs all those different functions. And the antenna is this collage of very pretty pictures show you that antennas come in all sorts of shapes and sizes. Here's a Tradex antenna out at Kwaislein. It's a dish antenna. That dish is a parabola, and the energy comes out of the source here. And here's an antenna that looks like it's a hexagon, and that's made up of thousands of dipole antennas. And that antenna steers electronically rather than mechanically like this one. And here we see a close-up of the face of another phased array antenna. This is a phased array antenna. It steers via phase shifting. Here's a picture of that whole antenna. Then there are other antennas that are strips of circles. And here's a spirally antenna and another. They come in all shapes and sizes. If you fly out of, in Boston area, Logan Airport, there are air traffic control antennas. And this antenna is rectangular shaped, not circular. And that means that its beam in elevation is much broader than its beam in azimuth. In fact, shaping goes on so that this antenna has a very wide beam, wider than the geometrical shape of the antenna would allude to in elevation than in azimuth. Okay? And we're going to look at a lot of these different kinds. And also, if you look up here slowly, there are two antennas up here, two little parabolic dish antennas that have feeds out at their focus. We're going to get into the properties of all the that's sort of a big picture introduction I'm giving to you of what antennas look like. Okay, now let's just go over the fundamental concepts of antennas. The first one I'm going to show you is that, and I'm taking probably the simplest antenna, and it's just a dipole. You have two wires coming out with an electric field between them, and then they go off at right angles for a quarter wavelength in one direction and a quarter wavelength of another. The total length of the antenna that comes off perpendicular after the wire goes out. The total wavelength is half a wavelength. It's a very efficient way of transmitting, and it's called the dipole. And this is a simulation of an electromagnetic wave coming out of a dipole. And areas of high intensity are in red, and the lowest intensity in blue, and in medium are in this greenish yellow. And you see that the antenna has some directivity, maybe 80, 90 degrees. And it's a sinusoidal wave coming out. Just like you drop a pebble in a pond. And you'll see a wave go out, electromagnetic wave. Okay? And we're seeing that you drop a pebble in a pond, now we're repeating dropping the pebble in the pond. So you see it has a shape to it. A dipole has that shape. But also energy goes backwards. Some energy, less energy, goes backwards. So there's going to be a real issue. How do we concentrate the energy? A dipole is a simple antenna, but it doesn't have a lot of directivity. How do we generate more directivity? It's an interesting question. And again, notice we're oscillating an oscillating source is driving this dipole. Okay? Okay, now let's focus on what is antenna gain. I've talked about collimating, What do we mean by the gain of an antenna? Now, if we take a source that radiates in all directions equally likely, we call that an isotropic source. And if it was an electromagnetic wave that was emanating from that source, here we have an ideal tower, and from it just a source on top emitting radiation in all directions. This would be an isotropic antenna. Isotropic means going in all directions. Most antennas are directional. They send their energy preferentially in one direction. And the amount of energy that they send out, the power density that they send out, more in one preferred direction over that of the isotropic direction, the isotropic energy density, is what we call the gain. And here we see, in this case, and I'm going to explain to you how parabolic dish antennas work, we have a source, and the energy goes back to the parabola, and it is reflected out, and most of the energy goes out in one direction. Some goes in these little bumps we call side lobes. We'll talk about that later. And some goes off in other directions. But it's a lot less. And the amount of energy, of radiation intensity, over what you get from an isotropic antenna is what we call the gain. The overall power is the same. the overall, so many watts went out in all directions, equally likely, but a lot more watts went in this direction than went in other directions, even though the overall average power that the transmitter put out is the same. And so the gain is the radiation intensity over that of an isotropic sphere. And, okay, now let's look at that dipole again. The exact equation for the gain of the dipole is this a trigonometric and algebraic expression that's a little complicated. But here we see is in green we have the isotropic antenna, and in red we see the gain pattern of a dipole. And the dipole is located on the z-axis, up and down, again a quarter wavelength up and a quarter wavelength down. And there are a couple of ways we plot gain. We can plot it in a polar scale, where we take a slice, a vertical slice along the say the z x-axis. Since it's symmetric, it doesn't matter as long as the slice is downward through z. And this is what we see for the gain in red. And here we see, in this case it's blue, the gain of the isotropic antenna. And we see that the gain, the maximum gain in natural units, is 1.64, is the gain of the power intensity of the dipole over isotropic. And if we put that in logarithmic units, and the way we do that is we take that number, we take the logarithm to the base 10 and multiply it by 10, and that comes out to be 2.15. And so the gain in dB is 2.15 dBi, which means decibels over isotropic. If you forget what dBs are, you can go back to the first lecture where we defined what a decibel was. And we see here plotted, and in most of the plots you'll see in this lecture, we plot the gain in a logarithmic scale. These isn't in linear units. These are each 2 decades. This is a factor of 10. So here we're up at 2.15 dB over isotropic as the center gain, and here would be in blue the gain of the isotropic antenna, which is uniform over all angles. And here in angle, this would be 0 up on the z-axis, up straight up. This would be 90 degrees, and 180 degrees would be down the bottom. Okay? So the purpose of this view graph is to get you comfortable with understanding what these plots are. We're going to see more of them later. Now, let's go back to that parabolic dish antenna. Okay? With a parabolic dish antenna, it has the property that if you take energy, if we take a dish, we take a reflector, and we shape it in the shape of a parabola, we make it in the shape of a parabola. And that's just the distance out this way is the distance here squared. And that shape, y equals x squared. That's the shape of a parabola. If we make it in the shape of a parabola and put at the focus of that parabola a feed, then the electromagnetic energy will come out of the feed and go up in this direction, that direction, all these different directions. It'll hit the feed, hit the reflector, and bounce back out, and it has the property that all the rays will go out parallel. Okay? And the path length from the feed to the dish and out to a point out here will all be the same. So the path length will all be the same, and all of the different rays will constructively, they'll all add up. And when you look out at far distances, you'll see an antenna pattern that looks like this. Okay? And this is for a diameter of the dish. If we looked at this dish, it'd be circular, and this is a cross section of the dish. the dish's diameter of 5 meters, a wavelength of 300 meters, a frequency of 300 megahertz, and a wavelength of 1 meter. And for that frequency antenna, we'd have a gain pattern as follows. We'd have a peak, it'd be collimated, and the top of the antenna gain pattern we call the maximum gain. And that is, for this antenna, 24 dBi, or 24 dB above isotropic. Okay, that's over 20 dB would be 100, 4 dB would be, like about 3. So it's about 300 times the directivity, the gain, of an isotropic antenna, approximately. Now, how wide is this beam? The way we characterize the width of the beam is we go down from the peak, 3 dB, and then we measure how wide the gain pattern is. And it's the half power. When you go down half power, that's 3 dB. It's the beam width. It's the edge of the gain pattern to the edge of the gain pattern, right, left, when you go down 3 dB. And in this case, the half power beam width is 12 degrees. Now, as you go to the left and to the right in angle of the beam, we come down and we go where it seems to almost go to 0, and that's called a null. And then it goes up to and then down. And this bump here and here and here are called side lobes. They are places where we get local maxima of energy, but not at all anywhere near the energy that you want to have in your main lobe. What you'd like to do ideally is to have just about all your energy up here in a relatively narrow beam and very, very little energy down here. And it has to do with how we design the antenna in the feed as to what we get for side lobes and structure. Now, what happens is that this feed sends out energy, and some of the energy can, when we illuminate the diameter out to here, some of it can go out to the edge and around the back. So we can even get energy all the way over at 90 degrees over here, but it's way down in amplitude. Okay? So we've gone over what the side lobe is. The side lobe level is 18 dB, and that's from the peak to the top of the first side lobe. And the side lobe level is the distance from the peak of the first side lobe down to isotropic, 6 dBi. Okay, and you can see these two, the 18 and the 6, add up to the 24 dB, which is the whole size. Now let's move on and ask, well, how do I calculate what the gain is? And the gain is just 4 pi times the area of the antenna, the effective area of the antenna divided by the wavelength of the radiation squared. And that's the gain of a parabola, a parabolic antenna. And the rule of thumb in the best case is when you're very, very efficiently getting all your energy from your feed into the parabola, and the effective area of the parabola is all of the area. If you put in what the diameter is, pi d squared divided by 4, plop that all in, then you see that the gain is pi d over lambda squared. Now, notice that the gain increases as the aperture becomes what we call electrically larger, that the diameter is a large number of wavelengths. That's about the key thing. When we have the diameter, a large number of wavelengths, we get a very, very, very well collimated beam. Now, over here on the right, we're going to look at the effect of aperture size on the gain for a different number, for different wavelength antennas. And let's just look in this case, and we see as the frequency increases, as we go from 300 megahertz to 3 gigahertz, which is 3,000 megahertz, a factor of 10, we move up considerably from 22, 23 dB for say a 6-meter diameter dish. We move up to in the region of 40, 45 dB. We move up quite large. Okay. Now, to give you an example, which is very poignant, here we have two antennas that are out at the Kwaislein missile range in the Marshall Islands. And these antennas are radar antennas. And this antenna, the picture doesn't do it justice. This antenna is so big. Well, how big is so big? Would you believe 46 meters across? Okay? This antenna weighs 880,000 pounds, 440 tons. And it rotates in azimuth on railroad tracks. It's that big, okay? And it operates at VHF, about 150, 160 megahertz. Now this other antenna over here has a 13.7 meter diameter dish under this radome. A radome is a structure that you use to protect from the elements, an antenna which structurally may be delicate, but it allows electromagnetic energy to pass through it with very little loss. And this just shows you the radome, and in it at approximately that 13.7 meter diameter. Now you might think that this, because it's got a big diameter, it's going to have a big gain. But the fact is here, the wavelength is 1.8 meters, and this radar over here, MMW, stands for millimeter wave. Its wavelength is 0.0086 meters. Its frequency 35 gigahertz. The diameter's electrical size is 25 wavelengths for this antenna, and that gives you a gain when you plug the numbers into 34 dB. But this antenna has an electrical size of almost 1,600 wavelengths, which a gain of 70 dB. 3.5 orders of magnitude, 7 orders of magnitude. A 2.8 degree beam width, 0.00076 degrees, like a thousandth of a degree, a little smaller than a thousandth of a degree. So it isn't the physical size of the antenna as much as the electrical diameter, the electrical size, that makes really all the difference.